All right. Thank you. It's good to be here. Yakir, it's good to see you again after the 10 years we enjoyed the previous one that you were here. Happy birthday, Yakir. The full Cheshire Cat gets to welcome you to your 91st birthday. This basically what I'm going to talk about today was inspired by super oscillations. And basically one of the things I was doing is about a year ago, Andrew Jordan and Akim Kempf were meeting together. I'm not sure where you were. You were like...
You're in Italy at the Super Oscillations Conference.
You're in Italy at the Super Oscillations Conference. All right. And so they started thinking about, well, for example, you detect landmines with super oscillations, and I'll tell you what the motivation was for that. But the idea was, can you use a super oscillating frequency to excite resonant material without actually being resonant? Or could you pass through a resonant material without actually disturbing that material? So I started just thinking about super oscillations in an RLC circuit. Okay, so basically I use this very simple form of the super oscillation, cosine omega t plus I times 4 sine omega t raised to the 4th power. And this is what the function looks like. And this is the little super oscillating term down here. And basically if you just expand this out, it's an offset, a first harmonic, and a second harmonic. And the offset basically makes it so that the super oscillate, this term is centered right around 0, and it looks just like a fast peak. But the problem is you get these really large side lobes on the side, whereas the fast term is quite small. And this really bothered me. By the way, this was... I thought it was fun that we both had the same cartoon here. But I was just pleased that you guys were all still around at the end of the day, because my brain is feeling like that. I feel like I need to be excused. So the reason why that bothered me is because this is, for example, what the absorption of electromagnetic radiation looks like in water. And what you can see here is from about 1 megahertz to 100 megahertz, it's flat. They call this in GPR, ground penetrating radar, they call this the plateau. And what that means is basically the absorption is constant over that range. But if you go beyond about 100 megahertz, it starts to go up rapidly. The absorption becomes very strong. So I thought, well, maybe what we could use is super oscillations where we generate our for example, our base frequency and our second frequency, our harmonic in this region, but then have our super oscillating frequency up here. The problem was the absorption that I would get here was a lot smaller than the actual size of the super oscillating signal. So I felt like I was competing against the power in the side lobes versus the absorption in these peaks. So that's a little bit of the background. So basically in the overview of my talk today, I want to talk a little bit about Rayleigh resolution, then what is range resolution when we talk about remote sensing. Then I want to talk about frequency versus resolution, and interference, why it's good, why it's bad. And then going way beyond the standard range resolution bounds that people set. So when we talk about the Rayleigh criterion, it's a fairly straightforward idea. Basically, if you have 2 stars that are, and the light from those 2 stars is passing through a finite aperture, right? We put some sort of finite aperture. That finite aperture, when you go through all of the calculations, it basically gives you a star with an airy disk. Okay, it gives you this point source, then becomes an airy disk. And if you look at it in one dimension, what you get is the airy disk of one star and the airy disk of another star. And you say it's resolved when the area disk of one star is in the first minimum of the area disk of the other star. So what that, you get these at the first minimum, basically what you can think about, when this peak is at the first minimum of this other peak. So when I have a star, and I can resolve those two stars when it's based upon the area disk. But that area disk is a function of the size of the diameter of the aperture. Since Rayleigh, this is how people have been defining defining resolution. But there was recently some work by Mankei Tseng and now plenty of other people, in fact, some in the audience, Ephraim and Andrew, for example, where they went beyond this. They said, well, let's decompose whatever this new waveform is with this multi-star waveform into different modes. And then I can just decompose those onto those modes, look at the mode structure, and then I can say, oh, I know that can't be a single star. It has to be two stars. Here's the distance between those stars, so on and so forth. So this is a decomposition method. Okay, so now let's go to the next topic, radio ranging. What is radio ranging? Basically, you have some sort of radar antenna. It sends out a pulse, and that pulse hits off some target. The time of flight from the antenna back to the antenna is the round trip time, is your ranging time. And there are many ways of doing this. This can be a simple time of flight. There are also FMCW, in which you're just giving a linear chirp in the frequency, or there are matched filters where you're basically every 180 degrees you are randomly but importantly putting a pattern of phase distributions on a signal. And all of those you can do what's referred to as pulse compression and get various ways of finding distances and to targets. So okay, so that's how you do ranging, but what is range resolution? So when you think about range resolution, you think, oh, well, that's how well I can, what is the distance that I can resolve? But range resolution is how well can you resolve the distance of two objects in the distance. So a classic example is, so let's suppose you have two airplanes over here, and these two airplanes have slightly different distances relative to the antenna. And if you have a pulse, for example, you send out a pulse, these two planes which are flying in formation, they would come back with a single pulse. Whereas these two planes, because the pulse separation between them would give you two different peaks, you would say that those two planes are resolved, but these two planes are not resolved. And so when you think about range resolution, what you're saying is you're sending out directed energy to a particular direction of the sky, and in the same line of sight or within the same angular resolution, you have multiple objects, and you want to be able to get the longitudinal resolution of those multiple objects. So basically, what you can say is, well, if I have a pulse length tau and I multiply that by C0, divide by 2 because of the fact that it's round trip, then you can say it's resolved when the distance between these is greater than equal to C tau, where tau being the pulse length. But more generally speaking, this is the true range resolution because you can also do pulse compression. So C over 2 sigma, where sigma is the bandwidth of the pulse. So for a Fourier transform limited pulse, we know that these two are obviously the same thing. Okay, and that's been the case for basically since radar's been invented. You don't do better, you don't resolve better than C over 2 sigma. That's the law. That's what you're taught in radar school. That's what you're taught if you're going to do radar engineering. That's the law. That's even come down to LiDAR. They say the same thing. So why should we care about this? Basically, what it means is if I want higher resolution, so if I want to not just know, for example, are there two planes, but I want to know where's the cockpit relative to the nose, are there missiles on this plane, so on and so forth, then I want higher resolution, but in order to get higher resolution, I have to have high bandwidth. In order to do that, I have to have high central frequencies. So what the problem with high frequencies are, for example, in ground penetrating radar, you get strong absorption, just as I was showing you earlier. With stealth technology, for example, you have high directivity. In other words, well, I'll just show you in a little animation here. If you have a plane and you have some sort of incoming radar, if you have high resolution, then basically the incoming radar waves are just reflected off, and basically that is how radar is based. Yes?
I just wanted to ask how closely analogous this is to the Rayleigh problem. In the Rayleigh problem, if I have many photons, I can of course figure out things' position, not to the Rayleigh limit, but to that divided by root n.
Yeah.
But if you have two objects, as Manke showed, the information still goes to 0 when that separation is smaller. Is it really mathematically the same in the long term?
This is very similar, and I'm going to get more into that. So it's really what you're on is a point. If I want to know how precisely where that star is, then I can say, oh, if I measure a lot of photons, then I can do wherever that distance divided by root n. But the Rayleigh criterion for resolving two stars is independent of the number of photons. That was the beauty of the Manke-Tseng work, because now it becomes you can start thinking about it in different ways.
The Rayleigh criterion is independent of the distance, but
is independent of the number of measurements.
You could determine the distance. Still does go down with n. Except
The,
it doesn't go down as 1 over root n. It ends up going down as 1 over the 4th power.
You mean the precise position of the star?
No, the uncertainty I would get in determining the distance between the two stars, it still does drop with n, just not as quickly as the uncertainty in the position of a single object.
Okay, so that's an interesting point. Oh yeah, I forgot. This is independent of n. This measurement right here is independent of n, and that's how it's always been defined.
The Rayleigh criterion is a terribly simple one. It was developed when you had Bessel functions and so on. But it doesn't depend on that. It just says,
I know the criterion doesn't.
Is there a dip? That's all it's saying. Is there a
I know what
dip?
the criterion says. My point is that criterion alone is not the whole story for how accurately you can
Oh, of course not.
resolve two objects.
Sure.
But anyway.
Yes. I'm just drawing the parallel between these things, because basically that's C over 2 sigma is how it's defined in the range resolution radar and LiDAR limit. So now this is a big problem also in ground penetrating radar, because, for example, if you use 6 gigahertz ground penetrating radar, you can get centimeter resolution. However, you can only go down about a centimeter. You can't probe much more deeply than about a centimeter. So you get centimeter resolution at about a centimeter. If you go down to, say, 25 gigahertz, 25 megahertz, you can go 40 meters underground. The problem is you get meter sorts of resolution or higher. So this, as I was pointing out, is the ground penetrating radar plateau that people often talk about. It's often because there's water inside the soil that you're dealing with. So finding mines can be a very difficult thing. And the problem is the wavelengths that can probe to get mines are very low, that can probe down in the soil to see a mine are incompatible with the resolution to actually see a mine. So it's a big problem. So let's talk a little bit about band-limited functions. So, for example, here's a sinc squared. We've all seen a sinc squared. You can kind of think about it as it's a one-dimensional version of the Airy disk, if you want to think about it that way. And if you take the fast Fourier transform of it, what you see is that it's just a nice triangle, and you get this band limit that stops right here. So it's a band limited function, then there's a hard stop. And you know why a sinc squared works. You know that a square, for example, you take the Fourier transform of a square, you get a sinc, And if you're going to, if you have a sinc squared, you take it's basically the convolution of the square with itself, and you get this triangle, and so on and so forth. So now let's think about this in terms of, if I have a sinc heading off of these, a sinc profile function heading off these two planes, it's going to have two scattered elements. But radar is coherent. The waves sum. And because they sum, what you actually get is something that looks like this. Now this, in this case, this would show you that you actually have two airplanes because you get a resolved peak in the middle there. But what if I make this larger, right? What if I get the planes a little bit closer and the pulses a little bit larger? Then you get this, and this is the waveform that you get out. And so what's the answer? And you're not actually sure what's in there. Was it noise that's causing this? Is it you could imagine doing also a mode decomposition on this. But I want to show you a different way of thinking about this. These are what would happen for various levels of tau, where these are the separation between those two pulses that I showed there. So now I want to point you to a quote here. As I was studying through all of this, I found this quote here. It says, "Wave theory indicates that the best vertical resolution that can be achieved is 1/4 of the dominant wavelength. Within that vertical distance, any reflections will interfere in a constructive manner and result in a single observed reflection." In other words, everyone is thinking about range resolution in terms of time resolution. Can you separate these two pulses? So what about super oscillations? Can we do this with super oscillations? Well, super oscillations have locally faster oscillations, and everybody here seems to know quite a bit about those. And there are lots of different ways of doing this. One that I really want to kind of focus on today is one by Barbara Soda and Achim Kempf. And they have an efficient method for creating these super oscillations. And it's basically using band limit theory. And I basically went along and I said, well, let's just consider their super oscillations. And what I found out is that you could generate super oscillating functions, and this is a busy curve here, but basically what it shows is that this is a Gaussian. If I just had a Gaussian, this is if I had two reflectors with a Gaussian, I'd get this spread right here. But this is the band-limited function that I would generate using these super-oscillatory terms. And I could see a separation when I couldn't see a separation with the Gaussian. I see these two green pulses when I originally started with this blue pulse. But I started to get greedy. I said, well, let's get faster and faster oscillations. So I said, let's look at this situation right here. And here we have a super oscillation where we have a really fast term right here. Here's a Gaussian. Here's the Gaussian which is spread. But as I move this together, what I found was that it didn't separate laterally. It changed from going down up. And it's fairly obvious if you look at this for a while. For me, it took probably about 1,000 different figures before I realized, oh, maybe there's something interesting in this amplitude if I look at things going up and down rather than side to side. So rather than try and temporally resolve, what about amplitude resolve? Yes?
What's the difference between the blue and the green?
Okay, so the blue, this is the original super oscillating curve. This is just zooming in right on that super oscillation and seeing those fast rising walls. And the green is what happens if I take that super oscillating signal and shift it with respect to, so I have a super oscillating signal and I have a super oscillating signal, and I just shift them relative to each other. Yeah, so all I'm doing is, I can imagine I'm taking that super oscillating signal, hitting it off a target, but it hits off a second target as well. And then they come back and then they coherently sum. Well, the coherent sum doesn't give you a peak here and a peak here. it gives you this green peak going up. So that was the beginning. And then I started thinking, well, in weak values, when we did our original work with weak values, we used basically what's called a quad cell. And what that does is it takes all the power on the right, takes all the power on the left, subtracts them, and then and we divide by the total power on those two detectors. So I started thinking, well, maybe what we need to do is design a signal that doesn't change in part of the signal and that strongly changes another part of a signal, to design it to be just like deflection. Because we know that deflection is very close to the optimal estimator. This method of estimating the transverse beam profile is very close to the quantum Kramer-Rao bound. And what we basically found out is that if we could do that, we were like 1.28 times larger than the standard quantum limit. And so basically what we need is something that is part of the signal that is very robust to shifts, and a part of the signal that is very sensitive to shifts. So if I have a signal, I hit it off of something, and then I have a second object, and I add those two waveforms, I want a part that's robust and a part that's that's very sensitive to that shift. These are a lot of other things that people have done to try and beat this range resolution limit. And this is what we just recently came out in Physical Review Letters. And we just showed that we could get 100 times better than that inverse bandwidth and get down to 20 micron resolution, even with waves that are meters in length. And so what we did is we considered three types of waveforms. We have our original sync squared waveform, this band-limited waveform. Then we have this waveform right here that was made with band-limited theory. So it was the follow-on of the super oscillations, but now we just used band-limited theory to generate this waveform, and then just a simple line interpolation. Now, why do this? Well, what we're doing is in this region, there is very little change as I shift a signal. This region has very little change. This region has very little change. And, but these regions of steep slope have dramatic change. So these are regions of zero gradient, steep gradient, and so we can define basically what you could think about is we send these signals out, they hit off of these two different distance objects, they go back into a single waveform, but with modifications to it. But rather than do this in free space, you can do this all in cables with a lot lower noise. And so what you're doing is essentially you're adding this wave to this wave, and when you do that, the height of this peak does not change, but the height of this does because of the interference. And if you then take basically do the same thing of what we were doing with beam deflection and define a parameter here where we say AC max over AC minus AC min over AL max minus AL min, we can get a very sensitive measure to changes in the relative heights of these curves relative to these unchanging portions of the curve. So basically this comes in, they sum, and what you get is these curves here with these very small changes. So how well can we do? Well, with this range resolution, with this triangle wave, we were able to get down, if you just take the relative bandwidth of this system, we could do 100 times better than the standard range resolution. Yeah?
So I'm getting confused between two different applications.
Yeah.
One is the detecting two planes, the other is the ground penetrating radar.
Yeah.
For the ground penetrating radar, I thought the whole point is that you have to use band-limited functions in order to be able to penetrate the ground. So these triangular waveforms are not band-limited.
That's right. That's correct.
So does that mean
Yeah, so the reason why we wanted to use the band limited functions is because we could force it to be within a band limit. But then we thought, well, you know, let's go all the way. And you know that when you have a triangle function, you have an infinite series of frequency terms. And with that infinite series of frequency terms, then that is somewhat a little bit cheating, because you can get really, really sharp resonances. Now, or really, really sharp features. And what we're actually doing now is basically showing that the highest frequency in that term sets the resolution of this ground penetrating radar. So if you start truncating that triangle wave, wherever you start truncating that triangle wave, it sets the resolution of how well you can determine the object. So that is a problem, because if you're, but what we were trying to show is that if you just take the Fourier transform of this triangle function and define it how it currently is in the literature, we're actually doing far, far better than the inverse bandwidth of that. Yeah, so what we're doing, when you say dominant frequency, what they usually define in the radar literature is they say 3 dB down of your peak. And so if you define 3 dB down, we're talking about, you know, 40 dB down of these little tiny features. So anyway, there's a lot to explore there, but.
Maybe you should mention the data is with the band limited function.
Yeah, so this is actually with the triangle function. This is with the triangle function, but this is with the band limited function. So as you might expect, the band limited function has a well-defined, you know, first and second derivative, and because of that, what happens is it has a quadratic beginning on there, and so it doesn't resolve as well, but you can still go well below this. When it gets to 1, that would be what we would normally call a resolved signal. And you can see here that we can already resolve better than at about 0.1. Yeah, so this is my S. This is the parameter where you have the ratio of the heights of those center peaks to the heights of those lobes on the sides. Basically what it's showing is as I shift those two signals and then interfere them and plot that parameter that I'm defining, that parameter goes down like this for the band limited signal, and it goes down linearly for the triangle function. Yes, so what this is the, I have to be a little careful with this. What this is basically saying is this is the ratio of the shifted signal to what we would call the Rayleigh criterion, or basically where we could say that we had resolved these two signals temporally. So if I put in a temporal signal, or which is basically the C over 2 sigma. So if I have C over 2 sigma, then when this is equal to 1, then I would temporally resolve the two objects that I'm looking at. But now what I'm talking about is anything less than 1 would not be resolved according to current definitions of temporal resolution. Now we're thinking about it simply in terms of time resolution, in terms of amplitude resolution. We're taking these peaks up here, this represents what S should look theoretically, and these are all experimental data points. And if you then zoom in on this region and you say, well, how well can I resolve an individual amplitude? In other words, suppose I have these two objects, but I'm moving them. So let's suppose this is the resolution distance, the temporal resolution distance of two objects, and now I have this distance between them, and I move the relative position of one of these in a distance that's very, very small compared to the Rayleigh criterion, then these are the individual amplitude resolved peaks, and they're very, very, very small. So we could resolve down to 20 microns distance, and we've actually done it now with frequency combs down to 500 nanometers with wavelengths that are of the order of 5 meters in length. So, which is 30 million times smaller than the wavelength rather than 1/4 of the size of the wavelength. So we're just trying to show that this new type of amplitude resolved paradigm as opposed to the standard temporally resolved paradigm. And but there's a whole lot more to this. Andrew's going to get to talk to you a little bit more about this. This is just the first of several things that we've done, but basically this is, for example, you can just think of 2-parameter estimation. When you start putting in different amplitudes for your 2 scatterers, they don't both have to be equal amplitude scatterers. If you have different amplitudes, then you actually get a slope here on your scattering. And we can now do, we've now done many parameter scattering, many different amplitudes, many different peak distances, and showed that this technique can resolve them. So I'm just going to tell you a few things that we're doing now. So one of the things that I talked about was that we had these band-limited functions, and that Howard is pointing out, we can use these, let's force ourselves to use band-limited functions, because then we can say that can go into the ground. And then use, instead of this simple parameter, let's use a maximum likelihood estimator. And we've shown with this that we can actually do quite a bit better with a maximum likelihood estimator for these band-limited functions. And it looks like there might even be critical phenomenon where suddenly you get a sharp drop-off in the strength of in how well you can do it. Anyway, so there's multi-parameter estimation, deep subwavelength imaging. Normally, when you think about imaging, you think about, I want to resolve everything by pixels. But whatever applies in the radar can apply also in optical. You can use optical techniques just the same way. You can, for example, imagine coherently illuminating a sample and then looking at different locations around, looking how the waveforms have shifted, and you can get deep subwavelength resolution. So we're very interested in seeing how, for example, how many objects can we look at? Can we look at curved surfaces? Can we do all sorts of things that are still based upon not having good angular resolution? This is not like a multi-pixel detector. We have basically no angular resolution. And just using this by scanning the receiver relative to the transmitter, we can do deep subwavelength imaging. Free space 3D, ultra high subwavelength distance, 30 million times smaller than the wavelength. And interestingly, some of the things that Andrew might also talk about is yoctosecond time resolution in basically being able to remotely sense something using, for example, LiDAR at the shot noise limit, even with just a few milliwatts of power. Okay, thank you for your time. Ephraim.
So it's really beautiful stuff and very cool. It seems to me like you're doing at least 2 cool things. One of them is tailoring the pulses that you send out, and the other is cover signal processing, figuring out what to look at. And the only thing I'd say is I'd really be interested to separate those two and try to understand where the advantage is from. Because I think in the other side of it, that's one of the people who've glossed over a bit. So in particular, to know if you did smarter signal processing on just a standard smooth pulse, how how much better could you already do than those textbook criteria? I think you already could do better. And then really see how important is the tailoring of the pulse and whether it's band limited or not, all the rest.
In fact, Andrew is going to talk a little bit about that, and that's a really good point. Right now, our parameter space is really large, but you're exactly right. For example, can you take the sync squared, just use the sync squared, do maximum likelihood estimation on the sync squared, and be able to pull out the interesting information? And the answer is yes. Yes, you can. Right now, though, we're trying to see. We have such an enormous space to study that we're trying to differentiate. But that.
Ephraim, I'll talk about both of those things on Friday. You're all right on point.
Yes, that's very good. Yes.
You had some way that improved the resolution from about a meter by about 10 to the power 6, right? From a meter to a micrometer.
Yeah.
What's the parameter that allowed this? I mean, you started from super oscillations which were very mild, right? The ratio between the big peak and the small peak was about factor 10 or 50. What's the parameter that made it possible to improve the resolution by 10 to the 6?
Okay, that's an excellent question. What you can think about is radar in the past has been very averse to interference. Interference is a dirty word in radar. And I mean, even if you watch the movies, like, we're getting a lot of interference, right? We're like, yeah, give us the interference. Okay, so interference is really the key. And what you can think about if you're doing, for example, LIGO, LIGO is based on interference. And in fact, one of the things that maybe Andrew will show is that the shot noise limited measurement of these frequency comb estimators that we've been using actually give the same sensitivity per photon as an interferometer, CW interferometer. The problem with CW interferometers, though, is that you only get one wavelength of ambiguity. And here we can get very large pulse disambiguation.
What gave you a factor 10 to
And
6?
it's interference. The key is interference.
No, but it must be some parameter. I don't know what the ratio of the peak to the super oscillation frequency to the limited frequency to some power. There must be some.
So I should say super oscillations is not a part of this. Super oscillations just started us thinking in this route, but it has nothing to do with what we're doing here. Super oscillations was just a seed. It's like LIGO. LIGO is using wavelengths. Bill, come here. What's the center wavelength for LIGO? Is it 1064? What's the interference? What's the wavelength that's in the LIGO? Is it 1064? 1064? Okay, so here you have a micron where you're getting 10 to the minus 19, right?
You get 10 to the minus 19.
So your wavelength of your light is a micron, but you're getting sensitivity of 10 to the 19, 10 to the minus 19, right? That's your ratio because of the fact that you're using basically 1 over root n, but you're using power recycling and all these recycling methods with the Fabry-Perot and inside the it's just because we're using interference. And
so what gives you this huge enhancement over LIGO?
Interference. Because you can go well, I mean, if you think about an interferometer, the reason why is it goes 1 over root n, right? If you're thinking about it in terms of photons. And if you have 10 to the 16 photons that you take a measurement with, you have 10 to the 8 smaller than the size of the wavelength.
But what you're doing is perfectly classical.
It is, but so is
Photons that come in, if photon comes
so is most interferometry, right? And you're dividing by the square root of number of photons. So, but now what we're limited by is the noise of the detector, because when you deal with radar, you're dealing with a different noise floor than you are with shot noise. Basically, it's just because we're using interference. And we can talk about it more. And maybe I need to do it tomorrow because I think I need to catch a train. So.
I mean, it's well known that in the microsonic interferometer, so you get a small fraction of a fringe. You don't have to have a complete shift by one fringe. So that is
Yeah, it goes as basically 1 over root n, right?
But again, that's something similar where finding the position of one object can be done to root n times better than the naive resolution. But finding a separation between two close objects is a harder problem.
Yeah. So getting the distance to something, you can very precisely do. But getting the distance between those two somethings at that distance is much harder to do. Justin?
Very quick question. Turbulence?
Gotta love it. No, what do you mean?
So like nuclei amplification techniques are nice because they're fairly insensitive to a lot of noise sources. So in radar we have a lot of like turbulence and propagation distortions of pulses, which is going to affect the interference properties of those pulses.
Yeah.
Have you looked at how robust this is to those sorts of
Well, the beautiful thing about it is the interference is happening at two objects that are very, very close to each other, right? So it will distort the summed waveform, I agree, but it's going to have almost no effect on the interference that's going to occur between those because the distance is going to tend to be very small.
Right, but it would affect your estimator, right? Because if your estimator is expecting a particular waveform shape.
That's true. For example, if you do a Fourier transform of your signal and you find out that each part of your signal is getting a different shift, for example. Yeah, it's true. So what you have to do is you try to work in, for example, in GPR, where you have a flat gain, where you have a flat spectrum. You want to work in a plateau, right? That would be the ideal situation. So you want to put your band limit in your plateau.
But maybe just an additional comment. This is indeed follow-up work to the initial idea, but you can also, if you have knowledge of the dispersive properties of the medium you're working with, you can reverse engineer that and work out what the waveform distortion would be and use that in your maximum likelihood estimator, which I'll talk about on Friday.
Okay, any other? Oh, Yutaka.
Yeah, that's a similar question to just Justin. Is that how much to create on this? How much does the tip to the behavior to be changed to the waveform?
Say that again.
Yeah, that's how much change to the tip change, slightly change to the waveform. If that's the case, how much effect to that resolution?
There's one part I'm not sure I understood. Was
Now, in the slightly change to the optimal shape of optimal shape.
yes.
In the slightly change there, how much to change to that?
Oh, so if you modify the waveform, how does this behave? And I think that's going back maybe to a little bit what Ephraim's saying. Are there optimal waveforms, and how do things change when you change your waveform? And we still have an enormous amount of stuff to check. In fact, we're using new waveforms pretty regularly, and so in an effort to try and optimize the waveforms that we use, and maybe almost a little bit what Justin is saying, right? If you have distortion to your signal, how does that affect your signal? But it does a lot, and so let me just say this is all new for us, and because it's still relatively new, I think for most people, there's still a lot to process.
Yeah, thank you.
Okay, thank you.